So let's look at a roadmap towards something called the Euler Lagrange equation. Now what this is will become apparent over the next couple of videos. But let's stick with our example of the hanging rope. So we have a rope in blue here, and we know that the rope hangs in a particular manner such that it minimises a particular quantity. Now the particular quantity that minimises the gravitational potential energy. But we've seen in a previous video that in order to generalise this and get away from the idea of a rope, we could just say that there's some value here, S. Now we've been using the idea of S being minimised, but that might not be the case. It might be the case that S is maximised, or it might be a point of inflection. So if we were to say, for example, we had a load of functions along the x-axis here, and we were to look at the value of S for those functions, and we could say in the terms of a hanging rope that we might find one particular function y of x, which is here, which minimises the gravitational potential energy. Now in general though, this generalisation here, if it's not a hanging rope, it might be a case that we might have a function that instead of minimising the value, it might create a maximum. Or it might be a case that it generates a point of inflection. Inflection one way or a inflection the other way. But the thing to note about these is that in each instance the gradient is equal to 0. So what we really do is, rather than call it a maximum or a minimum or a point of inflection, we just use one term and we call it an extremum. Now what we'd have up here then is this general equation here, and we would say that the extremum S is given by this functional here. Now in the case of a hanging rope, what we're interested in is finding is, or for that matter any general extremum here for this equation, is we're trying to find the value y of x. So that's a function y of x, and we're trying to find that function that will generate this extremum. So in the hanging rope we're looking for the function that will minimise the gravitational potential energy. So how do we find this y of x? Well, what we could do is we could change the system somewhat and then look and see what happens as the system returns back to an equilibrium point. So let's say for example we take the hanging rope and we were to put our thumb on this part of the rope and pull it down to this new position here. Now whenever we do that, we can say in this instance we could look at two things that change. First of all, we can say there's been a change in position. The rope was there at that point, and now that point is moved to this point. Now there's another thing that changes. If we were to look at the tangent at that point there, then we would have this line in yellow. But if we looked at the new point here, we could say that the gradient here at this side has changed. It has become steeper at this side, and the gradient's changed here, it's become shallower. So the changes that occur due to us moving the rope from one position to another is a change in position and a change in gradient. And we know that we're back at an equilibrium position when we ensure that the positional change and the gradient change equals 0. For when they equal 0, we're just back to this original shape of the rope. So we could take these two things here, a positional change and a gradient change equal to 0, we could tie them up into one just big equation, and we'll just call it equation, and we can say it's in an equilibrium position whenever this equation equals 0. So what's the point in this? Well, the point is that the value for y of x is tied up inside this equation here. Now this equation is something called the Euler Lagrange equation, and it's somewhat simplified here in my description because we don't necessarily need to just look at a positional change and a gradient change. You could look at the rate of change of gradient, so in higher order changes as well. But for the moment we'll just make it simple and we'll just look at a positional change and a gradient change. Also, if you've seen this introduced in textbooks, you'd see it introduced via the Taylor series, but we don't need to get into that mathematical detail here at the moment. All we want to do is get some intuition as to what the Euler Lagrange equation is. And we'll get that whenever we derive a mathematical equation for position and a mathematical equation for the gradient, and this equation is called the Euler Lagrange equation. So thank you for listening. I'll get you on the next video. Goodbye.